Okay, so what remains then? In the previous video, we have illustrated using this relationship, which is our interpretation of the duration for a continuously compounded bond. If we know the duration measure and we know the change in the interest rate and the original bond price, we can predict for a small change in the interest rate the change in the bond price. Given the numbers we had up to now, a change of 0.2%, a reduction of 0.2% in the interest rate produces, using this duration model, should produce an increase, a change in the bond price of 74 cents. And when we take the 74 cents and add on to the original bond price, we get a value of 87.54. Now we can verify that that's correct if we go to the next slide and just re-estimate the bond price. Just take the numbers here and adjust from, originally we had 11%. We said that the interest rate was 11%. If there's a reduction of 0.2%, then that becomes 10.8. And if we discount at 10.8, the value we get here is 87.54. which is consistent with the value we get from the duration. We can check that here by running our estimation again. So we had originally 86.80. If we change the interest rate then in our C++ code by reducing by 0.2%, when we re-estimate the bond, the value should be 87.54. So we're getting 87.54 here again. Now so that holds. Second thing we might consider here is, what if we had a much larger change in the interest rate, not a reduction of 0.2%, but what if we had a reduction of 8% in the, so we went from 11% and we reduced the interest rate by 8%. So that would bring the bond price down to 122. So in other words, what if we change the interest rate, delete, and 03, semicolon, rerun. If we rerun the estimate here, the value we obtain should be consistent with 122.66, 122.66. However, the duration estimate that we were using, that if we take the effect of a reduction of 8%, so 0.08 reduction in the interest rate, delta y, multiplied by the original bond price, multiplied by the duration we estimated, that results in an increase in the bond price of 29.55. When we take 29.55 and add that to 86.80, we get this value of 116.35, which is out of sync with the 122.66, and of course, different to the value we have here, which is the true value. And this highlights one of the issues with duration. Duration works reasonably well for small changes in the interest rate, but for larger changes in the interest rate, because it's a linear model, a change in the interest rate underpredicts the effect of the change in the bond price. The bond price is non-linear, whereas the duration relationship is linear. This is a linear relationship, not non-linear. There's no quadratic terms here. And to make the bond price to make this duration more accurate, occasionally we would be prepared to use convexity, and we go to a second order type term, and in other words we're adding a little bit of like a quadratic term which makes the relationship non-linear. Now that will produce, convexity when introduced will produce a more accurate estimate for the bond price, but it's still also not completely accurate. And it just, after a while, becomes simpler perhaps just to re-estimate the bond. But the duration, in terms of our main interest, is the economic interpretation of this duration, is that it is a kind of industry measure of bond price sensitivity. Largely these measures were developed in the 1930s. If you go back to Macaulay and so on, the duration estimates that were being made were done in a period not even before we had algorithms that we could reliably run estimates conveniently with, and cheap processing power. Duration was a conceptual type framework developed prior to the arrival of the handheld calculator, and for a large book of bonds, having these sensitivity measures was very convenient. In today's terms, it's just as convenient to reprice the bond in a bond pricing type setup. Occasionally we use the duration as we may look at the duration of a book of bonds and compare maybe assets and liabilities and try to determine duration mismatch as a measure of interest rate risk. And that type of analysis is sometimes applied by regulators when they go into insurance companies or banks and want to scope out the extent to which a particular financial institution has a interest rate risk. If interest rates rise, do the assets fall more substantially than the liabilities? For banks, that can often be the case because the assets on the balance sheet of a bank are very usually longer dated, and what you typically find, if we come over here, if we increase the maturity of the asset, let's say it's a 30-year asset, right? We run this, typically the duration will increase, right? So we get a duration going up here at 9.58, so that the higher we tend to make T, particularly with the lower numbers, 10, 15, 20, right, the higher duration will increase. Also important here is the effect of the coupon. If we reduce the coupon, the duration would also increase. So if we reduce the coupon, let's say to 1%, and run this, the duration should increase as well. We might take note, 9.6. And if we reduce the coupon to 0 and run this again, keeping in mind this is a continuously compounded, we have, so unfortunately put in 150. So let's 15 run again, and this should be closer to 15 here. Okay, so 14.999, keeping in mind that this is also an estimate or an approximation to duration. Once the coupon rate becomes positive, non-zero, the value of the duration will tend to drop. Okay, so we start with 15, it'll go down to 12. When we increase this to 10%, the value will fall again. 10% increase the duration, the coupon rate, the value of duration tends to fall. Why? Because more of the payment is coming earlier. As you increase the coupon rate, less and less of the payment arrives later. More of the payment comes earlier. As a result, the duration drops.